comes experiment 5 and 6, where you are going to learn and study the factors affecting the rate of reaction. And this is the experiment title. Talking about the introduction first. The rate of reaction is the amount of a reactant used up or the amount of a product obtained per unit time. As you can see, this is the formula. Rate of reaction is inversely proportional to the time taken for the reaction to be completed, and this is the formula. And these are the graphs related to the rate of reaction. Generally, there are two types of reaction, which is slow and fast. Slow reactions such as photosynthesis and rusting, while fast reaction will be precipitation or neutralization. Okay, now factors. There are so many factors affecting the rate of reaction. In these two experiments, we are going to focus only the concentration of a reactant and the order of reaction, which these two will affect the rate of reactions. Okay, there are a few methods of measuring reaction rates. Observable changes. First, changes in the mass or concentration of reactants or product. Second, volume of gas produced. Third, change in color. Fourth, formation of precipitates. Well, I'm going to explain in discussion session about these factors, how they affect the rate of reaction. Well, the objectives of this experiment will be the investigation of the effect of concentrations of reactants on the rate of reaction between sodium thiosulfate solution and hydrochloric acid. Second will be the analysis of observable changes that will be happening when there's a chemical reaction. These are the materials and apparatus that will be used in the experiment. First, distilled water, stopwatch, conical flask, white towel, measuring cylinder, and sodium thiosulfate, hydrochloric acid. That's all you need. Thank you.
What we see here is 45 ml of sodium thiosulfate solution, which will be added to the conical flask. Note the towel with the cross mark. Next, we have 5 ml of hydrochloric acid, which will then be added. The stopwatch is also started immediately. And the time taken for the cross to disappear is recorded.
Press.
Next, 35 ml of sodium thiosulfate solution is used. And this time, 10 ml of distilled water is added. As before, 5 ml of hydrochloric acid is added again, and the time is started.
Press.
Then, the volume of sodium thiosulfate solution is further reduced to 25 milliliters. (20 milliliters of distilled water is then added. Next, the hydrochloric acid. Time is started. And then what happens next is the volume of sodium thiosulfate is further reduced to 15 ml. And the volume of distilled water is now 30 ml. The volume of hydrochloric acid remains the same, which is 5 ml. And as usual, the time is started.
Stop.
In the last part of our experiment, we now use 5 ml of sodium thiosulfate solution. (40 ml of distilled water is used now. And next, 5 ml of hydrochloric acid.
Then I'm going to wait for 1 hour.
So, our endless process of waiting. It's been almost 1.5 minutes.
Oh,
It's starting to turn cloudy.
yes. Come on, faster. Put some
Get ready.
I still can see the X.
Should be any time now.
Okay lah.
Alright, our time's up.
These are the elements that are going to be discussed in the discussion part. Equation. Sodium thiosulfate react hydrochloric acid to form sodium chloride, water, sodium dioxide and sulfur solid. From here you just cancel sodium ions, chloride ions to get the ionic equation. And sulfur precipitates is a yellow solid which returns the solution from colorless to yellow. Okay. Here comes the brief explanation, or I say hypothesis. As the amount of sulfur increases, the cross becomes more and more difficult to see. Finally, the cross disappears from view when a certain mass of sulfur is precipitated. Hence, the time recorded for the disappearance of the cross is the time taken for the formation of a fixed mass of sulfur, which can be explained by this formula. steps in procedure where you are required to find the concentration of sodium thiosulfate solution. Okay, so you can use the dilution method, which is this formula, N1B1 equal to N2B2, to find the concentration of sodium thiosulfate solution. After obtaining the readings, the concentration of sodium thiosulfate solution, you can start calculating the rate of reaction by following this formula, the reciprocal of the time taken for the cross to disappear. And accumulate all the data, and you'll get either this or this graph. This one will be just the concentration of sodium thiosulfate solution against the time taken for the cross to disappear. While this one will be the graph of sodium thiosulfate solution against the rate of reaction. Actually, the factors of concentration of reactant affecting the rate of reaction can be explained by collision theory. Increases in concentration of sodium thiosulfate solution will increase the number of thiosulfate ions per unit volume. This will cause the collision frequency to increase, meaning that there are more particles, right? So they tend to collide each other more frequently. And thus the effective collision frequency increases, and resulting the increase in the rate of reaction. That's all. Simple, right? From this experiment, I can conclude that the concentration is directly proportional to the reciprocal of time taken for the cross to disappear, which is the rate of reaction. So use this book, it helped you a lot. Thank you.
Okay, experiment 6. It's regarding the order of reaction. So now for our experiment 6, the main objective will be to determine the order of reaction with respect to sodium thiosulfate, which means when you increase the reactant concentration, which is in this case the sodium thiosulfate, of course the rate of reaction will also increase. So here we are trying to find the order of reaction, which actually shows the relationship between the concentration and the increase in rate of reaction. In both experiments, we use the same apparatus, but except that in the previous experiment, we used a conical flask. In this one, we substituted the conical flask with a beaker.
First, we have to prepare 50 milliliter of sodium thiosulfate by using measuring cylinder, and as well as 5 milliliter of hydrochloric acid. So, let's put the sodium thiosulfate solution into the beaker. Then it's followed by the hydrochloric acid. Start the stopwatch. Of course, swirl the beaker so that the solution mixes thoroughly. Okay.
In the next part of our experiment, we now use 40 ml of sodium thiosulfate solution. As usual, I'm pouring it into the beaker. This time, we will dilute it with 10 ml of distilled water. Then, before the stopwatch is started, I'll add the 5 ml of hydrochloric acid. I'll now swirl it. At the same time, the time is recorded. Stop. After rinsing the beaker thoroughly, we will now reduce the volume of sodium thiosulfate solution to 30 ml. I will now pour it. This time, we use 20 ml of distilled water. And lastly, the 5 ml of hydrochloric acid again. Time is started at the same time. Stop. Next, we now use 20 ml of sodium thiosulfate. ml of distilled water. First 25 here. And 5 more, which adds up to 30. And final step, the 5 ml of hydrochloric acid. Time is started. As you can see. Stop. In the last part of our experiment, we now use 15 ml of sodium thiosulfate. And distilled water. This time 35 ml. Hydrochloric acid.
Stopwatch is started. Lo Vivian the group.
Stop. Now we're moving on to experiment 6, in which the procedure is exactly the same as experiment 5, and it has been explained earlier on by Eugene, which is trying to determine the effect of reactant on the rate of reaction by observing the X mark on the thumb. So for here, the only difference is that we're trying to find an extra thing called the order of reaction. From this equation, which is rate equals to K, bracket, is supposed to be the concentration of the sodium thiosulfate to the power of X. K here is the equilibrium constant, which is actually a constant, and X here is what we're trying to find. It's the order of reaction. So to put it in simpler terms, what we can see is, for example, this chemical A, to the power of X, or example, another example is number 2 to the power of N. These two figures here actually represent the concentration of a chemical. So, for example, let's say our concentration, like for example for here, is 2 times. 2 times concentration. If the order is, let's say, 2. So, what will happen is, it will result in a 4 times rate. So let's say if a concentration of 3 times, will actually increase exponentially. That's how the pattern actually is observed. So, talking about the results of our experiment, we actually recorded the results in the table of decreasing volumes of sodium sulfate, which actually represents the decreasing concentration, and time taken for the X bar to disappear. And based on this equation, okay, order is X. So we actually try to find X now. So how do we find it? Because it's the power, we actually log the whole equation. So it will become like this. Log the rate equals to, since K is a constant, we only need time. This is actually the sodium sulfate concentration. And lastly, the K, which is actually a constant. So now we can find X. So after that, we actually log our results and plotted a graph to find it. This is our graph. Log 1000 over time, which actually represents the rate, against log the volume of sodium sulfate, which actually represents the concentration. The graph obtained was actually a straight line graph, and we actually plotted it in best fit. So it would actually look roughly like this. But due to some errors, of course, the value we obtained wasn't totally accurate. Okay, so based on the previous equation, we can see that it bears a lot of resemblance to the equation of a straight line. So in gradient form, the straight line equation will be y equals to mx plus c. M being the gradient, y and x being their respective values, and c is a constant. So for just now's equation, you can see the log rate equals to x. Okay, x here is actually the gradient and actually means the order as well. This is our x value from the graph. Okay, it's log the volume of sodium sulfate plus log k is actually the constant here. Okay. Then we can see that x here is actually the gradient. So how do we find the gradient? We can easily take the value and divide them by each other. So based on the calculations, we found that the gradient is actually 1.134. So now, although we already have the order here, to further clarify and to prove the fact that it is correct, we actually have to find k, because it might affect our calculations. So what we got here is this. Okay? We submit the x and the y values, and of course the m, to find k. We got log k is this number, okay? And actually, this number, which is actually negative 3.198 exponent negative 5, will result in this, okay? Which means that there's like so many decimal places. So I would say we can assume it's negligible because it bears it has a very little effect on the results. So therefore we can just, in layman terms, dump it. So based on our results of log k just now, you can see that the value is actually so small. So we can just assume that it's close to 0 and we can just ignore it. So, in conclusion, from this equation and from our previous calculations that I have just shown you, x is 1.134. This is for just now's value. If we take the different values that we have obtained, we will get an answer which is almost like this. Let's say maybe 1.1 something. So the trend that we see here is the answer is close to 1. So therefore, I can conclude that for our experiment 6, x, which is the order of reaction, is 1. Thank you.
Oh my god!
I